We'll move on to discuss the design and assembly challenges associated with E-band. Then I'd like to present some guidelines for cost reduction. We'll then look at production issues. And finally, I'll end by discussing what I see as the future challenges for E-band. So, why E-band? The honest answer is, it's because people love wireless data. Whether they're downloading videos, uploading photos to their Facebook page, or tweeting to their many followers, they can't get enough wireless data. The time was, people used to talk about what the killer app would be for 3G. Nobody does this anymore. Whenever there's data capacity available, people find a way. There are new applications being developed all the time, and the demand for wireless data continues to rise. All of this data needs to go somewhere. Now, with cellular base stations, this data is often transferred using microwave point-to-point links, and there is a huge amount of data to be transferred. E-band has a wide spectral allocation, 71 to 76 gigahertz and 81 to 86 gigahertz. That's a total of 10 gigahertz of spectrum. And it's available pretty much worldwide now on what's known as a light license basis. This means you often apply online, it costs maybe $40 or $50 for your license, and it's very quick, and you still get the benefits of a license link. A lot of infrastructure providers and users are very nervous of using unlicensed band for telecoms infrastructure. Practical data rates increase with operating frequency. Actually, the data rates increase with bandwidth, but the two broadly fall in line. You can see the little graph here, which is from a book by Jonathan Wells on millimeter wave communications. And the practical transmission speeds are on the y-axis, and the carrier frequency is on the x-axis. And you can see the higher the carrier frequency, the higher your data rate. This is why people are moving to E-band and developing E-band electronics, despite the difficulties. So, what challenges do we have in the design and the assembly? The first is component availability. There aren't a huge amount of components out there. It takes more time and it's more difficult to develop components at E-band. And component manufacturers are a little nervous about making that investment to develop components. They need to convince themselves that they'll get their return on investment. The availability of performance data for components, even when a component is available, the amount of data that's there for the end user is often very limited. Test equipment at these frequencies is very expensive. There's not a lot of it around, and manufacturers actually end up having very little data. We also even see this at 60 gigahertz. Component performance. Output power, that's one of the prime limiters. It's very difficult to get a large amount of output power at E-band. 20, 23 dBm, round about the maximum you can get at the moment from a single component. Noise figure. I think this is an overlooked parameter, but there isn't a lot of man-made noise around at E-band, and it's worth investing effort to bring that noise figure down. However, the noise figure that it's easy to get, it's not as low as you might hope. Linearity. This is both receiver linearity and transmitter linearity. We'll be using complex modulation schemes. We need adequate linearity to preserve modulation fidelity. Our transmitter needs to be operating linearly, and our receiver needs to be operating linearly. So, assembly. This is also a challenge. Surface mount parts aren't really currently available. People are working at it. Infineon recently released a 77 gigahertz automotive part in a SMT package. And it was a little bit easier. It only had one 77 gigahertz port, and they used a differential output. Both of those things makes life easier. But there's still a lot of parasitics to associate with, and you can't buy E-band components in SMT packages today. I'm sure that will change at some point, but in line with those SMT packages will have to come new assembly guidelines and processes. An ability to tolerate bond wire inductance. It doesn't take much bond wire inductance to kill your performance at E-band, so you need a strategy in mind to tolerate that. Suitable substrate materials. You need to take care, and we'll talk a little more about this. Unit-to-unit repeatability. This can be a killer. You don't need very much difference in the way you put together an assembly to have quite a significant difference on the end performance. So moving on to these challenges in bond wire inductance. There will be an interphase inductance, and you need to minimize it. Now, when you package your microwave circuits, the approach you take is to absorb that inductance into a low-pass filter. But for a given inductance, there's a maximum frequency into which you can make that filter work. So here's a graph showing how the inductance translates to upper frequency. So if you want to package something or assemble something up to 4 gigahertz, you need to get that inductance down to about 0.2 nanohenries. By the time we're at E-band, you can only really tolerate about 0.1 nanohenry. Now, just to give you an idea, a 0.1 nanohenry inductance equates to a single bond wire of a length of about 110 microns. It's very small. That's not a lot bigger than the bond pads. So, how do we minimize the bond inductance? We've got two options. The first is to use tape bonding. So rather than a wire, we use a tape. The second is to use multiple wire bonds in a V-bond configuration. And this works well when going from a die to a substrate, where the substrate width is much wider. And you can see here, this is an example of a 43 gigahertz assembly as it happens that we did a little while ago. And you can see the V-bond at the RF ports there. In this particular case, we just mounted the die onto a ground area, an area of grounded bias. That would be appropriate at E-band, but you can see very clearly the V-bond that I wanted to show. Now, the assembly approach to minimize this bond length, we can go for a die and substrate at exactly the same level, or we can do die-to-die bonding. This is a photograph illustrating die-to-die bonding. This technique works really nicely. Here we've got 3 tapes going from a low noise amplifier on the left over to an image reject mixer on the right. And you can see, as well as bonding the signal pad in the middle, we've also bonded the 2 ground pads. And this makes for quite a nice coplanar transition. And this works very nicely at E-band. So looking at substrate materials, we want to use a substrate with a thickness that's less than a tenth of a wavelength in the bulk of the material. Now I've collected together here on a table a few substrates to compare. Now 100 micron thick gallium arsenide, quite a high dielectric constant, although a thin substrate. And that has a maximum frequency of around about 84 gigahertz according to these rules. And indeed, 100 micron gas is used up to around about this frequency. A lot of ICs are now also available in 50 micron gallium arsenide, and that pushes up that maximum frequency. Alumina, once the favored substrate material for microwave components, that works up to about 75 gigahertz with a thickness of 5 mil or 127 microns. And that's not a particularly popular material any longer. Quartz is a nice material. It's got a dielectric constant of 3.8. RT Duroid 5880 works really quite nicely at millimetre wave frequencies, and this has been used for a long number of years. And the one gaining popularity right now is LCP, liquid crystal polymer. This is available in 100 micron thicknesses and 50 micron thicknesses. You can even get it in thicknesses of 25 micron. You want material with a lower dielectric constant. You no longer want a high dielectric constant to shrink down your circuit size as you do at lower RF and lower microwave frequencies. Having a lower dielectric constant pushes up the maximum frequency of operation for a given substrate height. And the physical size of any printed components, just simple things I'm thinking of at E-band, things like couplers and splitters and filters, these will all be larger and therefore less sensitive to fabrication tolerances. Some of these materials are hard, some straight, some are soft. Both can be used. The hard substrates are easier for wire tape bonding, or a little more brittle and easier to break. The soft substrates, they're more flexible, more tolerant and more difficult to break, but they are also more difficult to wire bond or tape bond to. So for the assembly of the ICs and the substrate, we've got two options. We can use pockets in the IC, in the PC material, in the substrate material into which we drop the IC. This photograph shows an IC dropped into a pocket into 5880 material. This is a soft substrate, and in this case, we had it pre-backed with metal. And when we cut the hole or the pocket into the substrate and drop the IC in, the surface is flush with the surface of the substrate. Or we can mount MMICs onto a carrier, and then we interconnect them. It's like shown in this picture here, which was actually something that was put together in 1998. But what you can see is a collection of ICs in cascade, and each end you've got a little transition to waveguide. That's an E-plane probe transition, and that's realized on quartz. And this is another approach. So looking now at how we might like to keep the cost down. First of all, use inexpensive SMT decoupling capacitors rather than single layer capacitors. And I'm not saying you should never use a single layer capacitor. There are occasions in the assembly where it might actually be useful. But what I am saying is, it isn't always necessary to use an SLC. SLCs work nicely at microwave frequencies. If you need a capacitor of 100 picofarads or 1 microfarad, then you don't really need an SLC. That's taking care of decoupling at lower frequencies, and an SMT component will often be more than adequate. And this photograph is from some trials that we did in order to prove this very point. Avoid coaxial connectors. You can get precision 1mm coaxial connectors that work up to 110 gigahertz, and they work nicely, but they're expensive. And the coaxial cable at this sort of diameter is also very lossy. Use a low-cost carrier substrate. LCP is a low-cost example, as is the Duroid. And keep the assembly as simple as possible. So use as few millimeter wave parts as you can. Don't have routing tracks there that can be avoided. Use custom MMICs. Now this might seem a strange point, and at first not obviously a way to save cost, but hopefully my next slide will explain this. The final point I'd like to bring out is the manufacture in very high volumes. And this is really the stumbling block. As soon as you start producing anything in high volumes, it gets cheaper. So why would we use custom MMICs, and how could it save us cost? Well, the current pricing for an E-band LNA is around $100, actually just over $100 in 5,000 off quantities. It's easy to get this pricing off manufacturers' websites. I know that if I had an IC of the same size manufactured using a commercial available foundry, that IC would cost about $5 to manufacture. Quite a difference. These are my assumptions. A commercially available process on 6-inch diameter wafers, and for E-band, there's only really one process that fits this bill, and that's the 0.1 micron process of WIM semiconductor. A yield of 85%, that's a perfectly reasonable assumption. Area loss to the process control monitors of about 5%. All of the edge sites around the wafer loss. A test cost of 20 cents per site, pass and failed sites tested. Now, what I've not included is NRE, but the saving on the first 5,000 production parts is nearly $500,000. That's a reasonable amount of NRE. I'd be happy to develop someone an E-band LNA for that much NRE. So why are these E-band components so expensive? Well, we also need to include in the costs the amortized NRE I've mentioned, marketing and sales costs, app support, you provide app support if you're supplying components, profit. All your manufacturers should be allowed to make a profit. If they don't make a profit, they'll go out of business. Also, some ICs that are commercially available are manufactured on more expensive processes with smaller wafer diameters. However, all of these points together don't get you to reach that $100 part that's currently charged. Lack of competition is a big reason. Without competition, then there's no reason for people to lower their price. This is changing though. As more E-band parts become commercially available, the cost will be driven down. So the key to producing low-cost millimeter wave circuits is custom integration. These are a few examples of things we've done here at PlexTech RF integration. The one on the top left is an E-band image reject mixer. It's a subharmonic component, so you only need an LO frequency at half the mixing frequency. And this part's actually currently available through TriQuint. There's a 60 gigahertz amplifier, an E-band DVA, and an E-band driver amplifier. These are just some examples. All of these were actually done on a low-cost process. It's actually a 0.13 micron process in this case. And that process isn't suitable for PAs, but for all these components it is, and that's a 6-inch diameter wafer process. So, production issues. This can be a real killer, coping with unit-to-unit assembly variation. You need very tight control, a lot of precision in your assembly. The unit-to-unit variation of the E-band components, this depends on the E-band components, but you can, depending on the design, see some reasonable variations in production spread, and you'll need to account for these. Production test. E-band equipment is very expensive, and justifiably so. It's never going to be produced in huge volumes, and it needs to be more precise in what it's trying to measure. Accurate measurement is also more difficult, and these add to the cost and complexity of the production test. Now, I'd like to end by looking at or considering the future challenges. Managing cost expectations. Time and again, manufacturers of E-band radios will be asked, why is my E-band transceiver so much more expensive than my 38 gigahertz transceiver? And that is a difficult thing to get across. To the end user, they do nominally the same job. So the E-band transceiver can transmit at a higher data rate potentially. It's a shorter range, but nominally they're doing the same thing. We also need to think about managing customer perceptions, because in actual fact, the capital cost is actually greatly outweighed by the operating cost of a base station. And we need to persuade the network developers that they should realise that and not try and beat the poor old radio manufacturers up so much on the price. Nevertheless, we need to achieve cost erosion. The number of base stations is going up, so the number of radios are going up. Cell size is coming down. When people first put cellular infrastructure in place, they were desperate to keep the number of base stations down because base stations were so expensive. Now they're increasing the number of base stations because that's the way to increase the number of users that you can have on your network and therefore the amount of revenue you can make on your network. As E-band technology matures, the data demands will continue to rise and higher order modulation will be used. This means the output power of the PA will need to be higher in order to transmit the same power because you'll need to maintain linearity, and with a higher order modulation scheme, that means more backoff. The linearity of the receiver will also need to be higher, possibly architecture changes, possibly putting in some switched E-band attenuation. LO phase noise will need to drop. This could be a big challenge. It's quite difficult to meet the required LO phase noise even for a QPSK system at E-band. So that ends what I was planning to say. Thank you for your attention. I hope you found it of interest.